Hi, thanks for joining us today for the WindowMaster CPD, taking a look at intelligent natural ventilation. My name is Tom Lim, and I have responsibility for the WindowMaster companies in the UK and Ireland. My contact details are there, and they'll also be shown later on if I can be of support. I'm a mechanical engineer by background, and I've been with WindowMaster for just over 10 years now. And today I hope to share some of my experience with natural ventilation design of modern buildings. The agenda today is going to take approximately an hour. We'll have a quick look at WindowMaster and our background, how we've been involved with natural ventilation, research and design. We'll also take a look at perceived challenges of natural ventilation and how getting it right can really benefit buildings. We'll have a look at the basic principles, the advantages, the importance of control, how to achieve effective design and solutions, some final notes, and also a look at some example projects, as well as the opportunity to ask some questions towards the end. So a little bit of background on WindowMaster. Our roots go back to the 1940s, and the gentleman in the middle there, Willem Carnes Rasmussen, who invented the Velux roof light. As the roof light popularity took off, he was asked more and more often for something other than a big stick to open the roof lights, and so he set about designing the first window actuators to aid accessibility to open and close the roof lights. That became the electrical division of Velux, which then became WindowMaster, part of the Velux and VKR group, and subsequently we've been taken under private ownership back in 2015. Today, we have a number of different offices across Europe and in the US, with representation and support in the UK, Denmark, Norway, Switzerland, Germany, and in the United States. We employ more than 135 people, and we have approximately 1 million actuators operating in buildings around the world. We also have a number of certified partners that act as distributors and installer partners of our equipment. And we have a great deal of experience from over 1,000 major projects where we've been involved with turnkey packages, as well as the other projects where we've supplied components or design support. So as a business today, we focus on the design and manufacture of market-leading actuators and controls that are employed in modern buildings for intelligent natural and smoke ventilation. We have over 20 years experience with research and development, which has helped us become one of the foremost authorities on natural ventilation principles and the delivery of really effective building designs which integrate automation to help ensure that buildings perform as expected. We've worked in a number of research groups, including with the BRE, and regularly present at CPD technical conferences, as well as giving input to industry papers and regulatory frameworks. We also work with local authorities, architects and mechanical design consultants, as well as builders and subcontractors, to develop and build not just more effective solutions, but also more cost-effective solutions. Our product ranges include actuators, which are applied to the vents, and we have a whole range of technology there which is unique to us, such as MotorLink and TrueSpeed, which allows for position feedback, very accurate control, and near silent operation. We also have a range of motor controllers to suit either comfort or smoke applications, as well as a number of turnkey control solutions as well, which can be standalone or integrated within BMS systems and other control systems. So what is natural ventilation? Effectively, we're trying to harness natural forces to move just the right amount of fresh air through a building such that we can deliver really comfortable spaces which offer really good air quality. And what's the challenge? One of the problems with natural ventilation has been extensive projects using natural ventilation where they don't perform. Either they overheat or they have poor air quality. Issues with manual windows particularly have demonstrated that buildings quite often will not deliver the level of performance that the designers had intended. Similarly, there's a lot of issues with good design, but where the projects haven't been delivered as expected and the performance has failed. And also where automated windows have been employed, but the control levels have been poor, and subsequently there have been complaints about cold drafts, high energy use, noise, and those types of issues, as well as potential health and safety risks. We also need to consider security, particularly where we're looking at night cooling buildings. So having mentioned all of those challenges, why should we be using natural ventilation? The key focus for most modern buildings is energy consumption and carbon reduction. There's been lots of independent studies done to show that natural ventilation can significantly reduce the amount of carbon and energy used compared with mechanically ventilated buildings. Used in conjunction with mixed mode systems, we can also enhance the performance of those to reduce energy performance even further, particularly where we're looking at heat recovery systems. When we also take a look at capital costs, natural ventilation systems tend to offer a significant reduction in the capital costs compared with mechanical ventilation. And when we combine capital costs, energy costs, maintenance, and general running costs, we can see significant savings for natural ventilation compared with mechanical ventilation. You don't just have to take our word for it. The Carbon Trust did a really interesting study a few years ago, which is available online now, and they found that the energy consumption of those buildings which were effectively designed and delivered using natural ventilation demonstrated energy savings between 24 and 71% compared to other buildings of a similar type. They also demonstrated that those with effective natural ventilation solutions saved on average £30,000 a year on energy. Natural ventilation also forms a part of the London Plan, where it names passive ventilation as a primary driver for modern building design, wherever possible. There is a little artistic license here. However, I think it's a good point to consider where we would prefer to be breathing our air from in modern buildings. There's been a lot of studies done on mechanically ventilated buildings that demonstrate that often the mechanical systems aren't maintained to a high enough level, and subsequently there are significant symptoms within those mechanically ventilated buildings of sick building syndrome, and these tend to exhibit themselves such as dizziness, reduced concentration, fatigue, headaches, etc. This then results in reduced productivity in buildings, reduced capacity to learn in education buildings, and quite often increased number of sick days. The other beauty with natural ventilation is that we're utilising elements of the facade which are already there, such as windows, which means that we can reduce the amount of space taken up by plant and ductwork. So in summary, well-delivered natural ventilation can help us to reduce the amount of energy used, reduce the carbon impact. It can deliver much healthier environments compared with mechanical systems, and we can improve the performance to deliver really comfortable spaces which are more productive. All of this at the same time as reducing our capital and running costs. We'll take a quick look now at the basic principles of natural ventilation. So when we're designing the building, we'll consider things like wind pressure, which is going to help us to move air through the building, temperature differences and thermal buoyancy, which can help on very still days to ensure that we still get air movement through the building. And potentially we can look at some special designs which use things like south-facing chimneys or double-skin facades to move air around the building in a controlled manner. Typical guidance is that single-sided ventilation should be used in rooms of no more than 2.5 times the maximum ceiling height for the room depth. For cross ventilation, it's typically 5 times ceiling height as a maximum room depth. We would always recommend cross ventilation wherever possible. Single-sided ventilation is suitable for low occupancy cellular offices around the perimeter of a building, but we would always recommend cross ventilation wherever possible. And of course, if there's large open spaces such as open plan offices with atria, then we have the opportunity to use the atrium for stack ventilation as well. Night cooling is a really important element of effective natural ventilation design. By using the cooler air at night, we're able to reduce not just the air temperature of the rooms and exhaust some of the excessive heat buildup during the summer daytime, but we're also able to reduce the temperature of the fabric of the building, any thermal mass that we have available, and that can include chairs, books, tables, anything that we can, just to reduce it to a good temperature and an optimum temperature, such that the next day some of the latent heat being generated by solar gain and the occupants and equipment can be absorbed by that fabric to help to keep the air temperatures much more comfortable and reduce peak temperatures. On the right hand side here, you can see an example of a typical room that we've modeled, and the yellow bars show inclusive of summertime holiday, so that's typically for a commercial application that runs all year round, and the blue bars show a typical education development whereby they are closed during the summer months. You can see that with night cooling we can reduce the number of hours at higher temperatures over 26 degrees by half by implementing an effective night cooling strategy. That's a significant impact on comfort, and it can also help to reduce the peak temperatures in the room by around 10 degrees as well, depending on the building construction. Night cooling is a really important part of any effective natural ventilation design for modern buildings. There's lots of different components that are going to make up the overall strategy. So we may be looking at automated windows on the facade. There may be some acoustically treated louvers at the back of the rooms. There might be some clerestory windows, roof lights in the atria. We might have some roof mounted ventilation terminals in some spaces. And it's possible that we may use fans or other mechanical equipment which will be modulated purely based on a demand basis to minimize the amount of time that they're running, but to give a bit of assistance to the natural ventilation where appropriate. These might also be integrated as part of the smoke ventilation strategy as well, using suitable equipment. It's really important to understand the need for a stable indoor environment, and to understand that the demand for ventilation in the space changes during the day, as do the forces and the other components which are going to impact the ability to deliver that ventilation. So the demand for ventilation in space changes with occupancy. When the room's empty, obviously the demand for ventilation is relatively low, but with increased occupancy for classes, for meetings, then each person is giving off heat, and that creates a demand for ventilation to reduce higher temperatures. Equally, a lot of people in a space will be breathing out carbon dioxide, and we need to control the air quality as well. So as the occupancy levels in the room change, the demand for ventilation in the space is going to change. Also, thermal load in that space is going to change with equipment and with solar gain through the day. So the demand for ventilation in the space is changing throughout the day. Equally, the weather and the driving forces outside will also be changing. So the wind speed and the wind direction relative to the facades where we have opening vents will change, as well as the outdoor temperatures and also whether or not it's raining. So it's important that we try and track that change in demand with the changing conditions that are going to allow us to deliver the optimum amount of ventilation such that we don't upset the indoor climate. At any one time, there will be an optimal vent position. If we increase the vent position too far, then potentially we introduce drafts and cold problems and potentially heating demand. If we don't open the vents to the right position and they're reduced and there's not enough of an opening, then we can exhibit insufficient air exchange, and in those instances that can lead to overheating or poor air quality. Once we've understood that change in demand that we need to track, we also need to consider how air flows through vents. We carried out some research a number of years ago at the BRE using Velfat windows. Here you can see the test results, and it's probably best to focus on the top hung outward opening window, the green curve. At the bottom left there, you can see the results in a closed position at 0, and on the bottom scale, it's the opening distance or the chain length of the actuator as in different positions of opening. On the left there, you can see the volume flow rate of air with a typical wind speed applied to it. You might expect a linear scale, so as the vents close, then you would expect no airflow through it, and as you open it, it would linearly increase the amount of airflow through the vent. However, in a typical cross ventilation situation, such as this, where it's balanced cross ventilation, when you open the vents, the pressure differences either side of the vent actually create a much higher proportional flow of air at relatively small openings. So you can see that at only 10 millimeters of opening, you can achieve approximately 60% of the airflow through the open window. The importance of this is that when we're tracking the change in demand for ventilation in the space, we need to understand relatively small openings of the windows can deliver relatively high volumes of airflow, and therefore it's critical that we have the ability through the control system and the actuators being used to be able to open the vents to very acute and small openings according to the ventilation demand and the weather conditions outside. If we open them too far, for example, even 50 millimeters in this typical situation of wind, then potentially we're going to be introducing relatively high volumes of air through those vents, which could cause discomfort, excessive energy demand, and drafts. So what are our options? We want to be naturally ventilating buildings, and the most common approach to this has been manual control. The problem with manual control, as has been demonstrated by a number of different research studies, is that quite often they don't deliver the level of performance expected at the design stages. It's a nice tick in the box for natural ventilation, and it's relatively easy for contractors to deliver, and it's a low-cost solution. However, the level of performance is only as good as the people that are in the spaces and whether or not they actually open the vents at the right time. The problem that we have, as we've seen in a number of studies, is that humans tend not to react to situations until it's too late. So typically we might wait until the space is overheating before we open the windows, and that may be in the hotter part of the days where we're actually introducing even more hot air into the space. We don't tend to preempt ventilation. We also tend to be focused on other activities such as learning or working in those spaces. So we really need systems that can automate in the background to be able to take care of these things. There was a study done a few years ago which looked at a typical classroom. It looked at the thermal performance model. It also looked at the CO2 requirements and typical weather model. And it demonstrated that in order to hit the energy figures and the thermal performance and the air quality, the windows would have to change position approximately 40 times a day. So if we said that there were 4 windows in a room, that might be 160 operation of those windows in order to achieve all of the energy figures, the comfort figures, and the air quality figures. That's just unrealistic. And I know that we often see traffic light systems in classrooms these days to help teachers to understand when windows need to open and close. But if those traffic lights are constantly changing colour, the likelihood is that the windows are either going to be left open too much of the time, in which case we get problems with drafts, poor energy performance that have been reported in an awful lot of schools, or we have windows which are left closed too much of the time, in which case we have overheating, we have problems with poor air quality. We also don't have the opportunity typically for night cooling where windows and vents are manual. There's also been some research done to show that in winter we are almost as likely to open a window if we're too warm as we are to turn the heating down, and thereby if we can introduce automation that can overcome that, then we potentially improve the energy performance of the building and reduce carbon consumption. But a research project done in Zurich, whereby we compared some very similar classrooms, some of which were using manual windows and some of which were using automated control. Here you can see the layout of the building, and we selected comparable classrooms and we monitored the performance of those spaces. What we were able to see is that those classrooms, as you can see in the right-hand bar of the graph there, the hand bar, compared with the automatic rooms, saw much higher temperatures for a lot more of the time compared with those rooms that were using automated windows. Similarly, in terms of air quality, those rooms with automated windows demonstrated really good levels of air quality all of or most of the time compared with those with manual windows. And at the same time, we were able to deliver a 15% energy saving in those spaces with automated windows compared to manual windows. One important element for natural ventilation is that it needs to be a holistic approach to the building. There's lots of different elements that are going to make up the success of the overall strategy, and that's why we're keen to get involved with the design teams to support that process early on and to give the benefit of our experience as well. Quite often we can actually demonstrate ways to save money as well as making sure that the right components and approach is taken. So how do we achieve effective natural ventilation? Well, one thing that has been proven is that intelligent control can offer a significantly higher level of performance compared with manual windows and hugely reduce the amount of carbon and energy used compared with mechanical ventilation alone. So we're looking at controlling windows based on indoor air temperature and CO2 levels, which are an indication of air quality, as well as having a consideration to outdoor air temperatures, wind speeds, potentially direction, and whether it's raining or not. And we need to implement a secure night cooling strategy to suit. We also want to be able to deliver a very intelligent control strategy using proven algorithms and a fine control of the vents to avoid drafts and excessive heat loss. And of course, on those very still days where there's no wind, we need to be able to achieve quite large openings and consider the maximum free areas that we can achieve through the vents to get enough air movement such that we can still deliver a good level of comfort and performance. Single source of supply is also something that contractors have fed back to us as a preferred, such that all of the components that are delivering the performance are joined and responsibilities taken by one party rather than lots of different parties. There are various different options for the control systems, but the complete solution needs to work in harmony and complement other elements of the building design as well. So what does good look like? Based on our experience, we like to look at high-level automated windows, potentially with low-level manual windows underneath. These may very rarely need to be opened, but on very still summer days, we might want to use those windows to increase the opening areas to be able to move air through the space. The majority of the time, however, the automated high-level windows will do most of the work at relatively small openings based on the airflow we can generate using wind speed against the facade. High-level automated windows have a number of benefits. They're safer, particularly in education applications. There's less risk to children, and health and safety is less of a risk when windows that are being automated are put at a high level. They're also more secure when they're being used for night cooling, which means that they are more difficult to access should someone try and attempt entry, even though our actuators have a holding force of around 3,000 newtons, which means that they are very secure. We can also better control the impact of drafts when vents are at high level. We've done lots of studies which demonstrates that a very acute control of vents at high level brings the air in at the hottest part of the room and mixes it at a good depth into the room before it falls to body height, which reduces drafts local to the window, as opposed to larger openings at low level, which can definitely introduce drafts and have to be avoided wherever possible. WindowMaster can give input on a number of different design and product solutions. In terms of the number of actuators that are required on vents, typically on aluminium windows, for example, you might need more than one actuator where vents are over 1200 millimeters wide. This is not necessarily about the force that the actuator can exhibit, it's more about the capacity to achieve a seal of the window when we're pulling it closed against the seal at only one point in the center of the window. Wider windows will flex a small amount depending on the profile being used, and we can help offer guidance on that, as well as certain other practicalities like the possibility of concealing actuators and the practicalities and risks around that, as well as wiring routes and other methods that we can use to make the installation as neat as possible and deliver a high level of performance, as well as being really quiet and delivering an effective level of control. So I think we've probably agreed that automation is a good way forward to deliver high performance natural ventilation. One of the most common methods of achieving this is using the BMS. However, some caution should be expressed. Automating windows alone does not necessarily ensure that you are going to deliver a high level of performance. It's really important that the right equipment is used that allows the BMS to control the vents very acutely, as well as a very clear specification for the performance aspirations and the components being used, as well as different operational expectations. Traditionally, there's an awful lot of different methods for BMSs to control automated natural ventilation. Use of 0 to 10 volt and time control methods quite often have very limited levels of performance. It's very much estimated, and it's very difficult for the BMS to know where the vents are. So delivering an acute level of control of vents at small opening distances is very, very difficult to achieve. It's also very complex to program, which means that the BMS may elect to have much larger increments of control. Most commonly, we've seen 25% incremental opening. But as we saw earlier on from the aerodynamic curve, 25% incremental opening could potentially introduce more problems than it solves as a result of too high levels of ventilation, excessive drafts, and potentially a heating demand. There's also the possibility that BMS systems would use noisy fixed speed actuators and potential health and safety issues, or the use of mains actuators, which have to have limited operation due to overheating risks of the actuator itself. And quite often, more basic BMS systems have issues with hunting between windows. The BMS doesn't know where the vents are, and the basic programming for night cooling, wind and rain, etc., can potentially limit the performance of the systems. Also, lots of different parties getting involved with the BMS. Who's the BMS provider, who's the BMS integrator, who's wiring the different components, whose components are they using. Potentially you have a lot of parties involved in delivering the system, and they need to be very carefully joined up. Otherwise, when they don't work, everybody's pointing the finger at somebody else. So it's important that it's a much more integrated approach, and that's very important to be specified through the design team. It is, however, possible to deliver really effective solutions using the BMS. Motorlink technology is something that WindowMaster developed many years ago, and this is specifically for BMS integration. This uses a combination between intelligent actuators with Motorlink technology built in and Motorlink motor controllers. These motor controllers are networked into the BMS system. They can typically control up to 20 actuators per controller, depending on arrangement and actuator type. It gives the BMS the opportunity to send groups of actuators to very specific positions on a percentage basis, 1%, 2%, very accurate control, and get position feedback from the actuators to confirm that they've arrived there, they're healthy, and they're happy. They'll also get feedback if the vent's been overridden. During those automated operations, the BMS can tell the actuator to operate very slowly and almost silently in the background. However, if there is a more critical function, such as rain or smoke, then the BMS or the control system can tell the actuators to operate much more quickly to protect the building and the occupants. Our actuators also have pressure safety function built into them as well. This needs careful consideration depending on the design of the building, and we'd encourage you to discuss this with us. But it is one of the most sophisticated approaches to pressure safety and entrapment risk available on the market. Typical system layout for BMS integrated controls, as you can see there, you would have the BMS network with its own wind and weather sensor. You would have temperature and CO2 sensors onto the BMS network, and then you would have the Motorlink controllers stationed at different positions around the building, wired out to groups of actuators, and each group of actuators can be independently controlled even though they're on the same motor controller. The BMS then can communicate through nominated addresses to each of those motor lines to control the groups of actuators to deliver a very high level of control, and very quietly too. The next level of control that's available is a proprietary solution, and WindowMaster have developed a number of turnkey packages. As part of our approach, we always like to get involved early on in the designs with the design team to help to develop the designs to make them the optimum level of performance and as robust as they can be, as well as supporting clear specifications. We also get involved with steady state calculations, and we can get involved with full dynamic analysis with buildings as well, although we tend to work alongside the design team to complement their activities. We also act as go-between between the different parties, architects and engineers and the contractors, to make sure that the final solution that's being delivered is joined up and as anticipated during the design stages. We also have the ability to commission, deliver and service those systems as well, either directly or through our installer partners. A typical turnkey system from WindowMaster may look like this, with a number of temperature-only sensors or CO2 and temperature sensors. Override keypads is something that we always encourage, as well as the controllers and the groups of actuators around the building. There would always be a weather station so that we know what's going on outside, and there would be some sort of head end or system panel, which is the brain which will do the decision making on where to send each group of actuators to. NV Comfort is an example of one of our compact systems, and this is typically suitable for smaller schools, office developments, or possibly larger houses, up to 8 zones. NV Comfort operates from a 7-inch touchscreen, which sits on a KNX network. It uses intelligent and proven algorithms to control windows and window actuators, and can also integrate with other devices such as heating, mechanical fans, and rooftop ventilation terminals. It's a really nice compact solution. It's quite cost effective for smaller projects. Our largest solution we call NV Advance. This is the top end solution, and this is used as a PC based head end with really sophisticated onboard algorithms to develop the highest level of performance for larger buildings, and we've delivered this solution as a turnkey package to hundreds of projects across Europe, from higher education and schools to large commercial projects. We talked earlier on about how complex it is to be able to control the environment to the optimum amount and to be able to control vents within a few millimeters according to the wind speeds outside and the demand in the room. CFD is a technology which is being used from everything to Formula One racing to building analysis and design. And CFD is something that we've adopted for NV Advanced to be able to deliver the optimum level of control. The CFD that we carry out is not thermal analysis, it's an assessment of wind pressure around the building from 16 different directions to see how the wind is impacting those vents that we're going to automate in order to optimize their position such that we get just the right amount of airflow through those spaces. It offers potentially a much higher level of comfort and reduces the amount of energy consumption in winter. A nice example is Hadley Learning Centre. Quite a complex building form, and as you can imagine, as the wind changes direction around that building, it can have a potentially significant impact on how the wind will affect the vents around the spaces, and making sure that we achieve the right level of ventilation into each of the rooms. So at the point that we are appointed onto the contract, we will get a full set of drawings of the site and the building, and we'll build up a 3-dimensional model for which we will then apply a CFD analysis of the wind pressure. The data from this file is then built into the head end and allows us to make decision making when there is a demand for ventilation of space. You can see the different rooms and spaces and the different wind pressure coefficients around the building there. Essentially, if there's a demand for ventilation of space because of air quality or temperature that's deviating or approaching the set points, then we'll go to the weather station, we'll see which direction the wind's coming from, how fast the wind is, and the outdoor temperature, and we'll use the data file to look up to see what the wind pressure coefficient is on the vents in that space. We then apply some fairly sophisticated and proven algorithms to select the optimum vent position such that we're trying to find the balance point of those vents, that we're moving just enough air through the space for it to be highly comfortable, have minimum drafts, and not create any excess heating demand, but it's delivering a space which is great temperature with really good air quality. We saw the aerodynamic test curve earlier on. Typically with our projects with MV Advance, the opening positions are on average as little as 25 millimeters. And you can see why acute control of those vents is really important to be able to deliver a balanced energy performance and comfort levels. So MV Advance is a turnkey package which is delivered either by WindowMaster or one of our installation partners. It uses proven control algorithms and really sophisticated CFD analysis for best building performance and comfort. It really does work hand in hand with a holistic design approach with the design team, and it also offers intelligent day and night cooling strategies as well to find just the right amount of ventilation during the day and night to optimize building performance. It also uses motor-link technology as well to deliver accurate control and whisper quiet automation. It also has the ability to interface with the BMS such that it can integrate with other systems such as hybrid and mechanical ventilation, heating and solar shading. Hybrid ventilation is something that we're getting more and more involved with. By using intelligent natural ventilation, we can help to reduce the amount of load on the mechanical system and the amount of running time. It can also help to reduce the size of the mechanical plant, and thereby it can actually help to deliver reduced capital costs with mechanical systems. Our latest technology is called MV Embedded. This is really the most flexible solution for all modern buildings using natural ventilation as a design approach. MV Embedded is completely flexible, and it uses our motor-link controllers, but with upgraded and onboard intelligence, as well as cloud integration possibilities. It uses proven intelligent control for natural ventilation and for mixed mode ventilation and integration with other components such as heating and solar shading, with onboard logic within the panels. It means that the system using MV Embedded can be standalone, operating vents to suit demands and the weather conditions using onboard logic, or it can be integrated within the BMS system. Because they're cloud-based, they can also be used for remote access and for secure online access to status and data through nice user interfaces like mobile apps or through Facilities Manager's head-end screen. As a standalone solution, no BMS is required. All of the intelligence is built into the controllers, and they can be configured to deliver a high level of control of the automated vents around the building, with the possibility of upgrading to CFD-based algorithms similar to NV Advance, without the requirement for a head end. It's a decentralized solution, highly stable, highly flexible, and very cost effective. MV Embedded can also be integrated as part of the BMS solution, forming a part of an integrated approach. MV Embedded controllers can still deliver the control of the vents, but they'll do it based on set points and instructions from the BMS to enable or disable the signal, as well as coordinating operation of the NAT vent with other systems around the building as well. Typical system topology for MV Embedded as a standalone system will have room temperature sensors, CO2 sensors wired back to the controllers, independent groups of windows around the spaces in different rooms, which can exhibit a high level of independent control for each group of windows, and weather station. As I said, the onboard intelligence within the controller will optimize vents that it's looking after, and the whole system is networked together to be able to share such things as time and weather data, and it's connected to the cloud so that we can look at cloud-based data aggregation and user interfaces. MV Embedded used in conjunction with the BMS basically allows the BMS to give some input and control over the MV Embedded system to tell it when it wants to operate and when not to operate for such things as holidays, and to integrate with other components part of the BMS are controlling. MV Embedded is built on proven components. It uses a new generation of our motor-link controllers that's been well proven over the last 10 years or so. It uses a dongle to be able to enable the onboard logic, but also to store zone information and naming criteria, as well as sharing information between different controllers. And we have a new indoor room sensor, which has got CO2 temperature and humidity capabilities, as well as an override keypad for that zone. We also have an app which is constantly being developed for occupants to be able to visualize the status of their zone, as well as having different levels of input to override the windows as well, depending on how it's set up through the central dashboard, which is really there for the facility manager or caretaker to oversee the system and to set certain parameters. WindowMaster are proactive, supporting the design process at the very front end of projects, but we also have a network of service engineers and certified partners who are able to help in the delivery, but also the maintenance of the systems as well, to make sure they're very cost effective and require minimal maintenance and downtime after they're installed. So top tips and final notes. Think about the best locations and opening distances required for the project. This is something that we're keen to give input on, and we can often find ways of cost savings and coordinating the different elements such as wiring routes, how the actuators look, the best actuators for the application, and to make specifications as clear as possible from a performance perspective to ensure that the building looks and performs the way that the designers would expect. Also consider wiring routes and containment runs, and quite often there's some nice neat ways of hiding these without making it difficult to maintain the system in the future or adding excessive cost in the initial build. Using smart actuators and proven intelligent controls is really critical to be able to deliver a high level of control for the actuators and the vents, such that they can be dependably operated at very small openings when they need to in winter, and have intelligent control approach for summertime ventilation and night cooling as well to optimize the building performance. All of this can help to deliver much more comfortable spaces and much higher levels of energy performance. Using smart actuators which have multiple speeds of operation can also help to reduce noise during automation, which is another common complaint with other actuators in the market. We would recommend using motor-link actuators which can operate almost silently in the background, particularly those which have got our new TrueSpeed technology. And of course, we have a team of experts that are always happy to take questions, phone calls, or to attend meetings to review drawings or project designs at any stages, whether that be early design stage or through in the build process. We have lots of examples on our website and over 1,000 projects where we've been deeply involved with the systems that are delivering a really high level of performance. Just some examples here, and more information is available on our website. The automation that we've delivered has been highly effective and very high performance, delivering comfortable spaces for those in office and learning environments. We've delivered automation to windows of all different types and sizes and orientations, and we're always happy to work with you on your projects and offer advice. Some examples of the projects that we've been involved with from the big, such as the tower at the PNC Plaza in Pittsburgh. This has got over 6,000 motor-link actuators, optimizing the environment within this incredible building. To the smart, the Harvard Center for Green Buildings and Cities. This is actually an old building from the 1940s, which has recently been upgraded using motor-link technology. And it's also a research room for low carbon buildings and house zero research. It's an incredible building. It's currently being used as a live study to ensure that natural ventilation solutions are as best they can be, and it will influence architectural guidance and that to engineers in the future as well, based on the performance that they can achieve in that space. We also have some really nice showcase projects such as the Crystal in London, which is the Siemens Urban Sustainability Centre, using our Motorlink technology. Moorgate Exchange in London. This uses a combination of WindowMaster actuators not only for comfort but also for smoke ventilation. And this building achieves nearly 30% less energy consumption than the current best practice and a 20% reduction in CO2 emissions. We've also got involved with some really tall buildings as well, such as the Skyline Tower in Munich. This building features over 3,000 WindowMaster actuators, which are concealed within the window system. And we've got involved with some pretty colourful projects as well, as including the Flame Towers in Baku, also Prime Tower in Switzerland with nearly 7,000 window actuators. We've done an awful lot of higher education developments, including this one in San Francisco at the university there, at the Center for Science and Innovation. The building and the intelligent natural ventilation is helping to deliver 42% energy savings compared with other baselines. And of course, there's lots of other projects that we get involved with. And here's one real world project that we've got involved with up in Manchester. It's a cost-effective, high-performance, naturally ventilated school, Rolls Crescent Primary School, which is in Hume or Moss Side. This was delivered over 10 years ago now, but continues to be a really effective solution. It uses our NV Advance. It has quite deep classrooms. Some of the spaces are pure natural ventilation. Others use fans, which we modulate to optimize the environment, but we've run the fans as little as possible to have minimum amount of energy use. And in a typical hot summer week, we're able to dial into the system and look at some historical figures. And you can see here that in September 2007, the hottest week of the year, and the peak temperatures were hitting 26, 27 degrees. Outside, however, the majority of the rooms were 22, 23 degrees, which is really comfortable, particularly in the height of summer, where much cooler than that, it can actually feel quite cold. CO2 levels in the spaces also really good. BB101 tends to use 1500 parts per million as a benchmark. We can set CO2 targets relatively low in automated buildings, and anything below 1,000 can be considered good air quality in classroom environments and highly occupied environments. There's lots of other information on our website at windowmaster.com in the reference section, and you're welcome to explore that.
We've also recently launched our new Actuator Finder tool that you can find on the WindowMaster website. It's a great tool for both architects and engineers. Input some simple window information and it'll give you a suggestion of actuators featuring our MotorLink technology, as well as basic free area calculations and other useful information. Why not check it out now and add it to your favourites bar for future reference.
I'd like to thank you for your time, and you now have the opportunity to send any questions to us. I would also encourage you to connect to us to keep informed and stay up to date with the latest information and useful updates. You can sign up to our newsletter at windowmaster.com, or you can connect with us on LinkedIn. You can find there the WindowMaster group or myself, Tom Lim. And you're also welcome to contact me directly at tly.uk@windowmaster.com, or you can email us at our central info email, info.uk@windowmaster.com, with any questions or for project support. Thank you very much for your time. I hope that was useful. Please feel free to contact us if we can help you with your projects or if you have any other queries. You can also now follow the instructions on the web page to ensure that you receive your CPD certificate. Thanks again for joining us.